This is Lesson 7, Solving Quadratic Trig Equations, and this lesson is from the Grade 12 Advanced Functions course, and we are in Unit 5, Trig Identities and Equations. So at this point in the course, you should be very familiar with solving this type of equation, linear trig equations, such as 2 times sine x equals 1, and you solve for values of x within a given interval. What we're going to do in this lesson is we're going to look at how do we solve a trig equation that has a quadratic trig function in it. And what makes a trig function a quadratic is if it is being squared. So we're going to learn how to solve equations like this. 2 times sine squared of x plus sine of x equals 1. And we'll solve for all values of x within a given interval. Usually the interval is between 0 and 2 pi. So make sure you click the link in the description, grab a blank copy of the lesson, and you can fill it out as we go along. So let's get started. Okay, before we solve a few quadratic trig equations, I want to go over a couple things with you. So first of all, when we solve these quadratic trig equations, we're going to solve for all the angles that satisfy the equation as long as the angle x is within the interval between 0 and 2 pi, including 0 and 2 pi. And because trig functions are periodic, make sure you know that there's lots of times when we're going to find multiple solutions to the equation. There's lots of angles that have the exact same trig ratios, right? Because trig functions are periodic. So be prepared to get multiple solutions. How are we going to solve these equations? Well, just like any quadratic equation that you're solving, we're going to use the same types of skills. We're going to set them to 0, we're going to factor them, then we're going to use the zero product rule to set each factor to 0 and solve from there. If it can't be factored, don't forget that doesn't mean there's no solutions to a quadratic equation. It just means you might have to use quadratic formula to find the irrational solutions. Also, another thing to be prepared to have to do is use identities that we've learned earlier in the course, such as Pythagorean identity, compound angle identity, double angle identities, because sometimes the equation that's given to you involves different trig functions, but we always want the equation to involve a single trig function so that we can use the skills we've learned from the course to be able to solve it. So we may have to use some identities to replace some trig functions with equivalent trig functions so that it's written in terms of a single trig function. And that's example 4 and 5. We'll get there near the end of the lesson. So once we've factored our quadratic and we've set our factors to 0, we're going to have linear trig equations to solve. And remember, when solving linear trig equations, we can use our special triangles. We can use graphs of trig functions or the unit circle. These two methods will help us get exact answers for angles. They'll get us exact values, so use these if possible. And if we're not able to use special triangles or the unit circle to get exact values for the angle, then what you'll have to do is use your calculator to get an approximate value. So these give you exact, and your calculator will give you an approximate value. And we always prefer exact values if possible. And I'll clarify what I'm talking about in these two scenarios as we do a few examples. Oh, and I put a reminder here about what the unit circle is. Remember, if we have a term arm that rotates some angle theta, the xy coordinates of where that terminal arm intersects the unit circle, right, circle with radius of 1, tell us the cosine and sine ratios of that angle. If we were to do cosine theta, that would equal adjacent over hypotenuse, x over 1, which is just x. So cos theta equals x. So the x coordinate tells us the cos theta ratio. And sine from theta would equal y over 1, which is just y. So sine theta equals y. So the y coordinate is equal to the sine ratio of the angle. So the xy coordinate tells us the cos and sine ratios of the angle as long as it's the coordinate of where it intersects the unit circle. So for example, this point right here, because it's a unit circle, is 0.01. So if I rotate pi over 2, I know sine of pi over 2 is 1. This is the sine of pi over 2 value. And this is the cosine of pi over 2 value. Because I know the x and y coordinates of where I intersect the unit circle, if I rotate pi over 2, I know the cosine and the sine ratios for pi over 2. Cos pi over 2 is 0, sine pi over 2 is 1. And same logic for these 4 points that I've labeled around the outside. I would know the x and y coordinates of all 4 of those points. Therefore, I would know the cosine and sine ratios of 0, pi over 2, pi, 3 pi over 2, or 2 pi. So let's go ahead and solve some equations. Let's get started solving some quadratic trig equations now. Example 1, solve each of the following equations for x being between or equal to 0 and 2 pi. So we want all the values of x that satisfy this equation as long as x is between or equal to 0 and 2 pi. So this quadratic trig equation is actually already in factored form. So I'm starting us off easy. It's already in the form something times something equals 0. So we can use our zero product rule that tells us the product of two things is 0 if either of those factors is equal to 0. So set each of those factors to 0 and we'll solve. So set sine of x plus 1 equal to 0 and set sine of x minus a half equal to 0. Now we just have to solve each of these linear trig equations that we've created, and we can use what we learned earlier in this unit to do that. So we need to isolate the trig ratio. So sine x equals -1, right? Just subtract the 1 to the other side. And now I need to know when is sine of x equal to -1. Well, it's equal to -1 an infinite number of times, but I just want to know for what angle between 0 and 2 pi is the ratio equal to -1. So I can use my unit circle to calculate that, right? Remember the sine ratio is equal to the y coordinate of where it intersects the unit circle. Let's look back to the unit circle. When is the y coordinate -1? Right here. So this is the sine ratio of 3 pi over 2. So sine of 3 pi over 2 must be -1, because if I rotate 3 pi over 2, the terminal arm would intersect the unit circle right here with the y coordinate of -1. So I know over here, the x value is equal to 3 pi over 2. And this is the only answer between 0 and 2 pi for this linear trig equation that we solved. If we were to imagine, let me go over to the unit circle. If we were to imagine a terminal arm rotating around the unit circle, how many times between 0 and 2 pi did it get to a y coordinate of -1? Well, it got as high as a y coordinate of 1, y coordinate of 0, y coordinate of -1 there, and then back to a y coordinate of 0. It only got to a y coordinate of -1 once. So there was only one answer between 0 and 2 pi for this linear trig equation we just solved. But how about when is this factor equal to 0? Because right, this product is 0 if either that factor is 0, which happens when x is 3 pi over 2, or if this factor is 0. And when does that happen? Well, let's solve this one. So let's set this trig ratio equal to 0. So sine of x equals a half. And now don't just automatically do inverse sine of a half, because if we do that, your calculator will give you an approximate answer. We can actually get an exact answer for the angle that creates this sine ratio using a special triangle. So remember your special triangles. This is the half equilateral special triangle. And I know that sine from pi over 6, right? Sine from here would be opposite over hypotenuse, a half. So I know sine of pi over 6 equals a half. But there will actually be two answers for when the ratio is at 0.5. Because if you remember your cast rule, you should know that a sine ratio is positive in this quadrant and this quadrant, the two quadrants where y coordinates are positive. So I have to take that reference angle, pi over 6, and place it in those two quadrants, because I know sine from a reference angle of pi over 6 would equal 1 over 2. So place the reference angles in the two quadrants where sine ratios are positive between 0 and 2 pi. So let me draw terminal arms in those two quadrants where both those terminal arms have reference angles of pi over 6. And I'm going to call the angle of rotation to this terminal arm, I'm going to call that x2. Right, I already have an answer over here. I should call this x1. That's my first answer for x. And then I'll call this angle of rotation x3. That'll be my third answer for x. And both of those angles have reference angles that are pi over 6. So I'll label those reference angles, pi over 6. And now I have to figure out what are the principal angles that take me to those terminal arms. So answer 2 for x. What's the principal angle? Well, since I'm in quadrant 1, the reference and principal are equal, right? From the positive x-axis counterclockwise to that terminal arm is pi over 6. So x2 equals pi over 6. And x3, the angle from the positive x-axis counterclockwise to this terminal arm, well, I fell pi over 6 short of going a full pi radians, so I would do pi minus pi over 6. Think of pi with a common denominator as this, so it would become 6 pi over 6 minus 1 pi over 6. That's 5 pi over 6. So I have three answers to the equation. I have 3 pi over 2, pi over 6, and 5 pi over 6. There are three answers to the equation. Any of those three answers would make this original equation equal to 0. And I'd encourage you to actually test it out and try each of those angles on your calculator to make sure it works. And let me just remind you that with this type of equation here, it's best to use your special triangles to get exact answers, because if I go to my calculator, I'll show you that it would only give me the approximate answer. Okay, making sure that I'm in radian mode. If I'm looking for what angle has a sine ratio of a half, you can ask your calculator by doing inverse sine of a half, and your calculator will give you an approximate answer for that angle, 0.52, so on. But we can do better than that, right? We can get the exact answer from our special triangle. We got pi over 6, right? Pi over 6 is the exact value of that decimal. See how they're equivalent? So we want to be able to express it as an exact value, so we use our special triangles when we can. If we can't use our special triangles because the ratio isn't in a special triangle, then you go ahead and do inverse trig ratios to get approximate. Part B, sine squared x minus sine x equals 2. So for this one, it's not in factored form. So this one's going to be a little more challenging than the first one we worked on. Often for these equations, I find it useful to use a let statement to replace the trig function with a single variable, so it's obvious that we have a quadratic. So we could say let sine of x equal, and then pick any variable, let's say k. If I do that, then my new equation says k squared minus k equals 2. Right, sine squared of x, make sure you understand that this really just means a sine of x squared. That's what it means. So when I replace each sine of x with a k, this changes to a k squared minus k equals 2. And then this equation that we've created down here, k squared minus k equals 2, well, that's easy to solve. This is a grade 10 type of equation. Just set it to 0, so move that 2 over. And now it's a quadratic set to 0, so we try and factor it, and if it wasn't factorable, we'd use quadratic formula. But let's try and factor this. This one is factorable. We're looking for numbers that multiply to the c value, so a product of -2, and add to the b value, so a sum of -1. And the numbers that satisfy that product and sum are -2 and 1. So we can split it into its factors. K minus 2 times k plus 1. And now that I have it in factored form, now we can resub in from our let statement what k is equal to. So remember, each k is actually a sine x. So this is actually sine x minus 2 times sine of x plus 1 equals 0. Now, this whole let statement isn't necessary. I just think sometimes it makes it easier for people to visualize that what we have is in fact a quadratic that can be factored. And then after you factor it, use your let statement to replace k with sine x again, and now we have our quadratic in factored form. So once we have it in factored form, we use our zero product rule that tells us we're allowed to now set each of those individual factors equal to 0. So, right, something times something is 0 if either that factor is 0 or if that factor is 0. So I'll set each of those factors to 0 and solve for what values of x make that true. And remember, we're only finding values for x that make this true between 0 and 2 pi. So when is sine of x minus 2 equal to 0? Well, let's solve this one by isolating the trig ratio. So sine of x equals 2. And this one, a ratio of 2 for a sine function, is actually not possible. There's no angle that gets us to a ratio of 2. Let me give you a couple explanations of that. Well, let's think about the unit circle. I know that the sine ratio is equal to the y-coordinate of where we intersect the unit circle. And when is the y-coordinate 2? Well, the highest the y-coordinate ever gets on the unit circle is 1. It's never up at 2. So the sine ratio can't be 2. Let me show you the graph in Desmos as well. So here's a sine function in Desmos. Look, when is this sine function have a y value of 2? Well, let me just draw in a horizontal line through y equals 2. So when does the sine function intersect that horizontal blue line? Never. The highest it ever goes is 1. Right? The trig ratios for sine or cosine are always between or including -1 and 1. So if we're ever trying to figure out for what angle is a sine ratio or a cosine ratio equal to a value that's either bigger than 1 or less than -1, we say it's not possible. No solution. There is no angle that would give us a sine ratio of any value bigger than 1 or less than -1. So there's no solution. There's no way this factor could be 0. How about this factor? How about the sine of x plus 1 equals 0? Well, let's set that ratio to 0. So sine of x equals -1. And then let's solve for what value of x, right? What angle gets us that sine ratio? And once again, we can use our unit circle for this. If we look back to the unit circle, when is the y coordinate -1? So for what angle would I have to rotate this terminal arm to be able to get it to intersect the unit circle at a y coordinate of -1? Right here, the same one as before, 3 pi over 2. Sine of 3 pi over 2 equals -1. So for this, once again, I say x equals 3 pi over 2. And that's actually going to be my only answer to this equation. There were no answers from this factor, and there was one answer from this factor. So 3 pi over 2 is the only angle that satisfies this original equation. I should also mention that once you got to this point right here, if you were doubting your understanding of the unit circle, you could use an inverse trig function, right, inverse sine, of -1 and ask your calculator what the angle is. It'll give you the approximate value of this, but then we could compare it just to make sure you're right. Let me show you what I mean. So if we did inverse sine of -1, the calculator knows your input is the ratio and we're looking for the angle, and it'll give you, actually as a negative value, but it'll give you 3 pi over 2. It gives you a coterminal angle to 3 pi over 2. Let me prove that to you. So coterminal angles are angles that have the same terminal arm, so I should be able to add 2 pi to this. And this gives me an angle coterminal to it, right? Whether you rotate 1.57 clockwise or 4.71 counterclockwise, it brings you to the exact same terminal arm. And that is equal to, let me show you that that is the approximate value of 3 pi over 2. So your calculator can get you the answer, but you can see how it's a lot more beneficial to be able to use our understanding of the unit circle to get the exact answer. Part C. This is another quadratic trig equation. I know it's quadratic because of the squared here. I have 2 sine squared of x minus 3 sine x plus 1 equals 0. So this quadratic is already set to 0. So what we want to do is we want to see if we can try and get this into factored form. And remember, if you couldn't get it into factored form, you'd have to use quadratic formula. But I think we can get this into factored form. I'll use a let statement again first, just to show you that this is just a quadratic that we could easily factor. So let me say, let the trig function sine of x equal some variable, I'll use k. So if I let each of the sine x's equal k, this equation up here could be rewritten as 2k squared minus 3k plus 1 equals 0. And now we have a quadratic that we would try and factor by finding numbers that have a product of a times c, so a product of 2 times 1, and a sum of the b value, so a sum of -3. And the numbers that satisfy that product and sum are -2 and -1. And then we have to factor this by decomposition, right? When the a value is not 1, we have to factor it by decomposition and then grouping. So we split this into -2k minus 1k. And I do that because those are the numbers that satisfy the product and sum. And then I factor by grouping. Take a common factor from the first 2 terms. So divide each of those by 2k. I get k minus 1. Take a common factor from the last 2 terms. So take a -1 out from both. Divide them both by the -1 and I get k minus 1. I have a common binomial of k minus 1. Divide that term and that term by the k minus 1 and I get 2k minus 1. So now it's been factored. Once you're done the factoring process, re-sub back in the sine x for each of the k's, because each of the k's actually equals sine x. So sine of x minus 1 and 2 sine of x minus 1. So this is the product that has to equal 0. Use the 0 product rule, which tells us we can then set each of those factors independently equal to 0. So sine of x minus 1 equals 0, and 2 sine of x minus 1 equals 0. So we want to solve these 2 equations. Whenever this factor is 0, it makes the product be 0, and whenever this factor is 0, it makes the product be 0. So let's find all the values for x that make either of those factors be 0, as long as the value of x is between 0 and 2 pi. So this first one is another one that we could use the unit circle to find an exact answer for. So when is sine of x equal to 1? Well, we're looking for when is the y-coordinate of where the terminal arm intersects the unit circle equal to 1. So let's look back at the unit circle. So our terminal arm starts here. How far do I have to rotate to get to a y-coordinate of 1 on the unit circle? Right there. I would have to rotate pi over 2. So sine of pi over 2 equals 1. So my answer for x to this equation is pi over 2. And let me just prove that to you on the calculator. So I'm showing you that sine of pi over 2 is equal to 1. And another way we could do this to prove this to you, right, if I were to trying to solve for the angle and knew the ratio, I could show you the inverse sine of the ratio. It should give me the angle pi over 2. Well, it'll give it to me approximately, right? It gives me that 1.57 approximate value, but that is what pi over 2 is equal to approximately. So using the unit circle, we get the exact angle that gives us a sine ratio of 1. Let me show you the graph on Desmos as well, just to make sure we're on the same page. So notice in Desmos, when is the sine function equal to 1? Well, right here at pi over 2. I mean, again at 5 pi over 2, but that's past 2 pi, so we don't want that answer. Right? It's equal to 1 an infinite number of times, but we want the only answers that are between 0 and 2 pi. So within that first cycle, the only answer is right there at an x value of pi over 2. Now let's solve the second factor being equal to 0. So we have to isolate the trig ratio. So sine x equals 1 over 2. I got that by adding the 1 and then dividing the 2. And now this ratio, we can get that ratio from a special triangle. Let me remind you of that special triangle. And also let me draw a Cartesian grid for you and label the cast rule. So from the special triangle, I know that sine from pi over 6 would equal opposite over hypotenuse, 1 over 2. So if I place a reference angle of pi over 6 in the two quadrants where I know sine is positive, right, because we have a positive sine ratio, I know that sine from the reference angles will give me the ratio of 1 over 2. So let me draw a terminal arm in both of those quadrants. And now let me label the reference angles. Pi over 6, right? Reference angle is angle between terminal arm and x-axis. So since this was my first answer for x, I'll call this x2 and x3. And I believe earlier in example 1, we already solved this equation, but we'll do it again anyways. So to get to this terminal arm, I would have to rotate pi over 6. To get to this terminal arm, I would have to rotate pi minus pi over 6, so 5 pi over 6. So I'll get two answers for x to this equation. So x2 equals pi over 6, and x3 equals pi minus pi over 6, which is 5 pi over 6. So I found three answers to the equation. Pi over 2 would make this factor become 0, which makes the whole product be 0. And pi over 6 and 5 pi over 6 are the angles that make this factor become 0, which also make the whole product become 0. So I'd encourage you once again to test out all three of those answers in the original equation just to make sure that you've gotten the correct answers. Example 2. So this is where our understanding of trig functions and trig identities and equations is really going to be challenged, but this is the very important part of the lesson. So this is part 2, use identities to help solve quadratic trig equations. In this example, we still want to find all the solutions to the equation within the interval between 0 and 2 pi. But the equation looks a bit different. It says 2 times secant squared of x minus 3 plus tan of x equals 0. There's two different trig functions here, a secant and a tangent. So we actually want to rewrite this equation so that we only have one trig function. So it's defined in terms of one trig function. So we'll look at our identity page, and we'll actually see that we can replace the secant squared x to be written in terms of a tan function. So let's look over at our identity page. And notice on this identity page, secant squared x is actually equal to tan squared x plus 1. And that comes from the Pythagorean identity, right? Dividing the Pythagorean identity by cos squared on both sides, it would get you this identity. So I can replace the secant squared identity. So I can replace this secant squared of x function with tan squared of x plus 1. So let me go ahead and do that. So 2 times tan squared of x plus 1 minus 3 plus tan x equals 0. So now notice this is an equation that's quadratic, where the only trig function is tan. So we should be able to go ahead and solve this now. So let me expand and collect here. So I'll distribute the 2 to each of these. So I would have 2 tan squared x plus 2 minus 3 plus tan x equals 0. And let me collect this plus 2 and negative 3 together. So I've got 2 tan squared of x. I'll write the positive tan x next. And 2 minus 3 is negative 1. Now that it's simplified, it's set to 0, it's a quadratic, we want to try and factor it if possible. So I'm going to use a let statement just to make that easier to visualize. So I'm going to say let tan x equal k. So that would give me 2k squared plus k minus 1 equals 0. And we want to factor this, so we're looking for numbers that have a product of 2 times negative 1, that's negative 2, and a sum of the b value 1. The numbers that do that are 2 and negative 1. So we split the middle term into 2k minus 1k. And then we factor from the first two terms, common factor from the last two terms, and then common factor the common binomial, and it's now in factored form. And then don't forget your let statement. Each of the k's is actually tan x. So what I have is tan x plus 1 multiplied by 2 tan x minus 1. And this is equal to 0. So now that it's in factored form, we set each factor to 0 and try and solve. So set tan of x plus 1 equal to 0, and set 2 tan x minus 1 equal to 0. And we'll solve each of these equations independently. So this equation, tan x plus 1 equals 0, isolate the tan ratio, so tan x equals negative 1. And now we want to figure out what angle would give us that ratio. Well, we can actually create the ratio of 1 from a special triangle. Let me remind you of that. So this is the isosceles pi over 4, 1, 1 root 2 special triangle. So we always want to use the special triangle to get an exact answer for the angle, if possible. We don't want to use the inverse tan ratio to get approximate values if we don't have to. So notice from this special triangle, tan from pi over 4 would be opposite over adjacent 1 over 1. So tan of pi over 4 is 1. If I place that reference angle in the two quadrants where tan is negative, so let me just draw the Cartesian grid here quickly, and notice that tan is negative here and here. So if I place a reference angle of pi over 4 in those two quadrants, then I would get the angles that will give me a tan ratio of negative 1. So let me draw those two terminal arms. So both of these terminal arms have a reference angle of pi over 4. Reference is angle between terminal and x-axis. So I'll label both of the reference angles pi over 4. And now I have to figure out what would be the principal angle to get me to each of those terminal arms. And let me just label the angles around the Cartesian grid. So I will call this one answer 1, and this one answer 2. So angle 1, angle 2. Let's figure out the principal angle to that one and to that one. So to get to angle 1, I would have to rotate not pi, I fell pi over 4 short of that. So I'd have to do pi minus pi over 4 to calculate angle 1. So angle 1 equals pi minus pi over 4. So 4 pi over 4 minus 1 pi over 4. Angle 1 is 3 pi over 4. And to get angle 2, I fell pi over 4 short of going a full 2 pi. So I'll have to do 2 pi minus pi over 4. So 2 pi minus pi over 4. So think of this as 8 pi over 4 minus 1 pi over 4 That's 7 pi over 4. So these two angles have a tan ratio of -1. And let me just verify that with you on the calculator. So notice that both tan of 3 pi over 4 and tan of 7 pi over 4 both have a tan ratio of -1, and both of those angles are between 0 and 2 pi. So we have found two answers to this equation already. And that's just from this first factor being equal to 0. How about the second factor being equal to 0? Let's solve this one over there, and let me just move some of my work from the other part over. Okay, so now let's solve this factor being equal to 0. So start by isolating tan. So add the 1 over, then divide the 2. So I've got tan x equals 1 over 2. I can't create a tan ratio of 1 over 2 from any angle that's in a special triangle. So notice from this special triangle, there's no tan ratio of 1 over 2. And let me remind you of the other special triangle just to prove to you we can't do it from there either. So pi over 3, pi over 6, 2, 1, root 3, right? Tan from here is 1 over root 3. Tan from here is root 3 over 1. Okay, so we're not going to be able to do it from a special triangle. So in this scenario, when you can't do it from a special triangle, we can't do it from a unit circle, what we're going to have to do is rely on the calculator to get an approximate answer. So we cannot get an exact answer for this angle, so we'll get an approximate answer. Where is that approximate answer going to be? That's going to be very important to understand because there are going to be multiple answers to this between 0 and 2 pi. There's actually going to be two answers. And where are those answers going to be? Let me just draw a Cartesian grid for you just to remind you of where tan ratios are positive between 0 and 2 pi. Tan ratios are positive in this quadrant and this quadrant. So when I do inverse tan of a half on my calculator, the calculator is always going to give you the smallest possible angle. So it's going to give me the angle in quadrant 1. But it's important to know that that's not going to be the only answer to this equation between 0 and 2 pi. Yes, there is an answer in quadrant 1, but there's also going to be an answer in quadrant 3 with the same reference angle. So let me label these answers, answer 3 and answer 4. So angle 3, angle 4. And then we'll use our calculator to get an approximate value for angle 3 and use its reference angle to get an approximate answer for angle 4. So angle 3 equals, so we would do inverse tan of a half. And we're only doing this because we cannot create the ratio of a half from a special triangle. So we have to rely on the calculator to get an approximate value. Let's do that. Inverse tan of a half. The calculator will give me an approximate value of about 0.46. So angle 3 is about 0.46 radians, and that's approximate. That's indicated by this symbol here. So I know angle 3 is 0.46, and since we're in quadrant 1, that tells me its reference angle is also 0.46. And I should label that reference angle, I'll label it beta. Beta equals 0.46. And now I know in this quadrant, if I drew a terminal arm that has that same reference angle, it'll have the same tan ratio. So I'll put that same reference angle, beta, which is about 0.46, this is approximate, in that quadrant. And then to calculate the angle from the initial arm all the way to that terminal arm, I would have to do pi plus 0.46. So I'll calculate angle 4. Angle 4 equals pi plus 0.46, and we'll get our approximate value for angle 4. So plus pi, and I get 3.61 approximately. So there are 4 answers to this equation. The first 2 answers make this factor become 0, and answer 3 and 4 make this factor become 0. But if either of those factors are 0, the whole product becomes 0, therefore all 4 of them are answers to the equation. And notice all 4 answers are between 0 and 2 pi. Part B, this is the most difficult one we've done yet, and you'll see why as we go through. So let me walk you through this one. This one says 3 sine x plus 3 cos of 2x equals 2. So once again, notice that it's 2 different trig functions. So we want to use some identities that we know to either rewrite the sine function in terms of a cosine function or rewrite the cosine of 2x function in terms of a sine function. Right? We want a single trig function involved in this equation. So what we're going to use is the cosine double angle identity. Let's look over to our identity page. And notice that cosine of a double angle can be written exclusively in terms of sine if we rewrite it as 1 minus 2 sine squared x. So let's go ahead and do that. So that would make this equation become 3 sine x plus 3 times 1 minus 2 sine squared x equals 2. So I just used the double angle identity to change this into this. And now that we have an equation written in terms of a single trig function, we can simplify it, set it to 0, and solve, right? Because this is a quadratic. So let's simplify this up a bit by distributing the 3 to each of those terms. So I would have 3 sine x plus 3 times 1 is 3, minus 3 times 2 is 6 sine squared x equals 2. And now I'm going to set this to 0. So I'm going to move all of the terms to the right this time because I want my leading coefficient to be positive. So 0 equals, take the negative 6 sine squared x, move it to the right. Take the 3 sine x, move it to the right, becomes a negative 3 sine x. And then this 2 is on the right side of the equation, but it's going to collect with the negative 3. 2 minus 3 is negative 1. So now that it's set to 0, we would try and factor this, and often I try and get you to do a let statement, let sine of x equal k. It makes the equation look less intimidating, and it makes it the work a little neater as we go ahead and try and solve this. So if I use that let statement, I get 0 equals 6k squared minus 3k minus 1. So this quadratic equation is set to 0. If we were to try and solve it, you'd first try factoring. Hopefully factoring works, but nothing multiplies to negative 6 and adds to negative 3. So factoring doesn't work. But that doesn't mean there are no solutions. We'd have to use quadratic formula to find the solutions. So at this point, when you can't factor it, try quadratic formula. So quadratic formula tells you that the variable, k in this instance, is equal to negative b, so 3, plus or minus the square root of b squared, so negative 3 squared is 9, minus 4ac, so 6 times negative 1. And this is all over 2a, so 2 times 6. So if we simplify underneath the square root, 9 minus this product, it actually becomes 9 plus 24, which is root 33. And this is all over 12. So this is what k equals. 3 plus root 33 over 12 and 3 minus root 33 over 12. Two possible answers for k. But keep in mind, each k is actually sine x. So sine of x could equal 3 plus root 33 over 12, or 3 minus root 33 over 12. So now we have two linear trig equations to solve. So I can solve these equations using my cast rule, and I'll need to use my calculator to get approximate values for the angle for these equations, because 3 plus root 33 over 12, I definitely can't make that ratio from a special triangle. So we use our calculator for this. But this is a positive ratio. I don't know what 3 plus root 33 is exactly, but I know when I divide it by 12, it's still positive. So based on the cast rule, I know there will be answers for angles that have that ratio in two quadrants, here and here. And I'll draw terminal arms in those two quadrants, and I know those two terminal arms are going to have the exact same reference angle. And I'll use my calculator to get an approximate value for those reference angles, but I know they're going to be the same reference angle. So to get, I'll call this one my first answer. I'll call that one my second answer. So to get the first answer, I'm going to have to ask my calculator, what is inverse sine of that, 3 plus root 33 over 12 ratio? And I know the calculator is going to give me the first answer because it always gives me the smaller angle if possible. So x1 is going to be about, let's ask our calculator. So my calculator told me the inverse sine of that ratio was about 0.82. So I place the reference angle, and I'll label it beta. Beta is about 0.82 there and there. And I know the reference angle is equal to the principal angle in quadrant 1, right? The calculator gives us the principal angle. It gives us the principal angle. But when you're in quadrant 1, that's also the reference angle. So angle 1 is 0.82. And I place that reference angle into quadrant 2 as well, and I would figure out that the second answer, answer 2, is going to be approximately equal to, we'll know that rotating all the way over to here would be pi, so we fell 0.82 radians short of that, so do pi minus 0.82, and it'll take you to that second terminal arm. So I need to do pi minus 0.82, and that'll give me an approximate value for the second angle. So let me calculate that. So I need to do pi minus that reference angle, and I get about 2.33. So 2.33 radians. So I have two answers so far. Answer 1, answer 2. How about from this equation? So 3 minus root 33 over 12 is going to be a negative ratio. Let me show you that. So notice that 3 minus root 33 over 12 is a negative value. It's about negative 0.23. So I know that this is a negative ratio, and I know sine has a negative ratio when you're in either quadrant 3 or quadrant 4, when you are down here in the two places where y coordinates are negative. So I'll draw a terminal arm in those two quadrants. Now, I don't know what their principal angles are, but I know they have the same reference angle in order for them to have the same sine ratios. And I can calculate the angles. I'll label these angle 3 and 4. The calculator is actually going to give me this one first because it's going to express it with the smallest absolute value as possible. So it's actually going to give me this answer expressed as a negative angle, which means in that direction. But keep in mind, the question wants the answers only between 0 and 2 pi. So if it gives us a negative answer, we actually have to express that as an equivalent coterminal positive angle. And I'll talk to you about that after the calculator gives us our approximate answer here. Right? So to get an approximate value for an angle that has this ratio, we can just do inverse sine of the ratio. So is it 3 minus root 33 over 12? So let's do inverse sine of that. And my calculator gave me negative 0.23. That means go 0.23 radians in this direction. So if I go 0.23 in that direction, that's given me the reference angle. The reference angle is 0.23 because it went 0.23 clockwise from the positive x-axis. But what is the angle from here all the way around to here? That's the actual angle 3 that I want for my answer. So what I need to do is I need to know that if this is negative 0.23, I can get a coterminal angle to any angle I want if I just add the period, if I rotate 2 pi radians, right? If I'm here and I rotate 2 pi, I'm right back to where I started. So all we have to do is add 2 pi to that negative angle. So let me add 2 pi to it, and I get an equivalent positive angle, 6.05. So this is also equal to 6.05 radians. If you were to rotate 0.23 that way, or 6.05 that way, you would be in the exact same spot. But the reason I want this one is because that satisfies the condition the question says. The answers have to be between 0 and 2 pi. So let me write down what the calculator gave us. The calculator gave us an angle of negative 0.23, about. But I actually want a positive angle, so I need something coterminal to that, so add 2 pi to it. And when I added 2 pi to that negative angle, I got 6.05. So 6.05 is the angle between 0 and 2 pi for this terminal arm here. And I should have these angles around the Cartesian grid labeled for you. Now I need angle 4. Well, angle 4, I know it's going to have the exact same reference angle as angle 3 had. And the reference angle for angle 3 was 0.23. So I'll put that same reference angle there, 0.23. And then to calculate angle 4, I would start at the positive x-axis, go counterclockwise past pi by 0.23 and get to angle 4. Get to that terminal arm. So angle 4 is equal to pi plus 0.23, right? Plus that reference angle. So angle 4 is about, let's do pi plus 0.23, pi plus 0.23. I'm going to get 3.37. So it's about 3.37 radians. So we have 4 answers. All 4 answers are between 0 and 2 pi, and all 4 answers would satisfy the original equation, which you can check on your calculator. Okay, so that's it for this lesson. I hope it was helpful for you. Make sure you download the practice questions and give them a shot, and that's it.